This is the screencast for section 3.7, example 5. We're going to find the second derivative implicitly. So the first derivative you're pretty familiar with. Don't forget, every time you take the derivative of an expression with a y, you need a dy dx. And now you can move over this x term and divide by the y term to get dy dx by itself. And I get that dy dx equals x squared over y. But that's not what we're being asked for. We're asked for the second derivative. That's going to involve the quotient rule. So I found the second derivative using the quotient rule on the first derivative. Now that expression though involves a dy dx. I want to be able to find the second derivative, the acceleration if you will, by just plugging in an x and a y coordinate. I don't want to have to mess with dy dx finding that too. So I'm going to use the expression I found for dy dx and plug that in. And now I can get rid of that denominator by multiplying the numerator and denominator all by y. And I get a fairly clean expression for the second derivative where all I would need to do is plug in the x and the y coordinate to identify what the value is of the second derivative at a specific point. The now try problem number 29 asks us to use implicit differentiation to find dy dx first and then the second derivative. So dy dx, I'll take the derivative of the left side, 2y dy dx because of implicit differentiation, and then equals 2x dx dx cancels, plus 2, again dx dx would cancel. Now I'm going to solve for dy dx just by dividing both sides by 2y, and those 2's are all going to cancel. So I get that dy dx equals x plus 1 over y. Now in finding the second derivative, I again am going to have to use the quotient rule. And I can't leave the expression dy dx in my second derivative, which, I mean, it got there because I took the derivative of y. So I need it, but I want to replace it. So I'm going to replace it with what I found dy dx to be, x plus 1 over y. And again, I'm going to get rid of the y in the denominator by multiplying the entire numerator and denominator both by y. And I have a fairly clean expression that I can just plug in an x and a y value for to find the second derivative, the value of the second derivative of our equation.